All right, thanks guys for joining me today with the permutation and cycles training. So we're going to go over three specific things today. First is drawing permutations as a graph. The second is finding the length of a cycle, and the third is finding the xth item in a cycle. A cycle of like 5 items, finding the third item. Now again, it's going to be more so in the way of like we're given this entire graph. There is one cycle randomly somewhere in the graph, and let's see the problems of like starting somewhere, go through and find the end cycle number from that location. This is a pretty commonly occurring thing that shows up in Silver. So we have three problems to sort of get to today. Two that we're going to get to. One is like if we have time, we'll sort of get to it as a ending problem. I will release the code and templates from this after the training. So it'll be up on the school group after the training, and it'll be available from today up until Sunday. So you'll have plenty of time to download that and get access to that. The reason I'm not publishing it right now is I don't want to distract you from sort of what we're going to be going over, but it will be available tonight until all the way until Sunday. So yeah, let's get into it. So we have three problems that we're going through. I'm going to put the first problem in the chat for you. Okay, so let's get into this problem. And our goal here is to talk about permutations and cycles, so we're going to really focus on that part of this problem. So let's just go through the sample input. I'm just going to sort of draw that out to demonstrate what we're going over today. Okay, so Farmer John has n cows, n is up to 10 to the power 5, and they stand in the line. Now what Farmer John does is he picks a pair of cows, and he has an m-step process, and in each of the m steps, he picks sort of a range and has that part reverse. So, for example, in the sample input, n is 7. So we have 7 cows. And then what we have is m equals 2, and k 2, and then k equals 2, or 2 as well. 2. So the ranges that are going to be reversed are 2 to 5 and 3 to 7. So we do this process 2 times, right? So the first time we do it, we're going to reverse the range from 2 to 5. So that's going to be this range here. And then we're going to reverse the range from 3 to 7. So that's going to be this range here. And we end up with this right here. And then we're going to do this a second time. Second time, again, the exact same thing. We're going to reverse the range from 2 to 5. And then we're going to reverse the range from 3 to 7. And we get this here. Cool. And I forgot to mention this earlier. If you have any questions as we're going through this problem, please put your questions in the chat, and I will be checking the chat to get any questions as they come up. If you raise your virtual hand, I'm not really looking at those right now, so please put them in the chat. And we're gonna have a follow-on conversation if you want to discuss later, but I'm gonna notice your question if it's in the chat. Okay, so how do we sort of start to approach this problem? Because this process, we do this, it's a k-step process, it's an m-step process, and we repeat it k times. So here k equals 2, but k can be up to 10 to the power of 9. So we could have k equals 10 to the power of 9 here, where we do this exact process 10 to the power 9 times. But we have this weird constraint where it's m is less than or equal to 100, and k is less than or equal to 10 to the power 9. So what do we do about this? Well, let's try to notice something interesting about this problem that we have here. So 2 starts at the second location, and it ends up in the 5th location. Okay. Oh, sorry. We want to know where it ends up at the end of the process. So at the end of the process, okay, sorry, I'm just trying to figure something out real quick. Give me 1 second. I apologize for this. Okay, cool. Okay, so yeah, 2 starts here, and then at the end of this process, it ends up in the 5th position. Okay, I believe we actually might have made a mistake when drawing out when drawing this out. Oh no, okay, sorry, we didn't. Okay, my bad. So yeah, the item that starts at the 2nd position here ends in this 5th position right here. The item that starts in the 2nd position at the end of the first cycle shows up in the 5th position here. That's interesting. Okay, let's try this again. The item that starts in the 3rd position before we do the first round, the 3 ends up in the 6th spot. The item that starts in the 3rd position here ends up in the 7th spot. Let's try one more. The item that starts in this 4th position, you can see the yellow, ends up here. 4th position ends up in the same spot. Just to sort of beat this in one more time, this starts in the 5th position, it ends up in the 1st position. Starts in the 5th position, ends up in the 1st position. So you might notice a pattern here that we have these starting locations for these items, right? Let's actually just draw them as circles. These 7 items. After we do K operations, they're going to end up somewhere else. So this one might end up like here. So yeah, we're going to have our new 7 after we do our M operations. Well, clearly, if we do this exact same M operations, the one that starts in this exact same location is going to end up in the exact same spot. So this way, so we don't have to repeat this exact same process K times. We can make it faster. Specifically, this is what we can do is we can say, okay, after the first operation, the elements end up here, and we're just gonna draw this out as a graph. So this is the permutation that the objects end up after one operation. We're just gonna draw it out as a graph. So the first item stays in the first location. So after M operations, this item will stay right here. The second item ends up in the 5th position. So after M operations, this item ends up here. The third item ends up in the 6th position. The 4th item ends up in the 7th position. The 5th item ends up in the 2nd position. So we got like a loop here. The 6th item ends up in the 4th position. Trying to untangle these as much as possible. And the 7th item ends up in the 3rd position. So just to draw this graph a little more clearly, 1 after one operation ends up here. 2 after one operation goes to 5. 5 after one operation goes to 2. 3 after one operation goes to 6. 6 after one operation goes to 4. 4 after one operation goes to 7. 7 after one operation goes to 3. This is sort of how they move. So if I want to know what happens if k equals 2, which is the sample input, so we can just test this out. What happens if every item moves 2 times? Well, if 1 moves 2 times, it's going to end up in the same spot. So 1's going to stay where it is. Cool. 2 and 5 move 2 times, they're going to end up at their same spot. 3 moves 2 times, it's going to end up at 4. 6 moves 2 times, it's going to end up at 7. 4 ends up at 3, and 7 ends up at 6. And as you can see, that actually matches our sample output. Perfect. Now here's where this gets interesting. What happens if k equals 101? How do we do it then? What we can do is we can actually take the length of each cycle. So this is a cycle of length 2, this is a cycle of length 1, this is a cycle of length 4. So what we can say is we're going to take k mod the length of the cycle to see how far we have to go. So k mod 1 here is just 0. So 1 is just going to end up at that exact same location, spot 1. Cool. Here we have 101 mod 2. That equals 1. So what that means is that it's going to go back and forth, back and forth, back and forth, back and forth. And every time we move 2 locations, we essentially just move 0. We end up at the same place we start. So really, instead of having to think about going 101 times, it's going to be the exact same as moving 1. So 2 moves to 5 and 5 moves to 2. Same thing here. Every time we move 4, it's like we just reset. So 101 mod 4 equals 1. So it's going to be like 3 just moves 1, 4 moves 1. Sorry, 6 moves 1, 4 moves 1, and 7 moves 1. And we end up in that exact same position that we started. No, I'm sorry. Not the exact position that we started. We started up in just moving 1 from where we started. So this is the power of drawing permutation as a graph. And I would go as far as to say whenever you see a permutation problem, okay, it may not always be a graph problem, but it usually is. So definitely draw it out as a graph and see if that helps. If it helps, great. If it doesn't help, hey, you just draw it out as a graph. You didn't lose much. So that'll help you sort of get started there. So that covers the first thing I want to cover today, like why do we draw permutations as graphs? The second, finding the xth item in a cycle. So here we still have the case where n is less than or equal to 10 to the power of 5. So if for every item we move k mod length forward to figure out, where it's going to reach. Let's say that we just have a big cycle of all the n items. We have a cycle of length n, and each item moves n minus 1 locations forward. That's still going to take us n squared if we do it naively. So we don't want to naively, take the steps n times. So what we're going to do instead, and it's going to be easier for this problem, it's going to get a little more complicated in the next problem, trying to do the exact same thing. It'll still work. That's why I want to start with the easy problem, then move to the harder problem. Is we're going to store the items in a cycle in an array. So what I mean by that is, how do we find the cycles in this case? Well, we're going to start at our location 3, or we're going to start at all our locations, and then we're going to just DFS to see where we get to. And if we reach something that's already visited, we have a cycle. So as we start at 3 and we DFS to 6, we're going to keep a vector or an array list in Java where we add the latest element to the back of it. So we're at 3, then we DFS down to 6, we add 6. We go to 4, we add 7. Then 7 goes to 3, 3 is already marked as visited. And I'm going to go into the exact implementation of this on the harder problem, because I think it'll be a lot more useful for you there. But just to sort of give you an idea, when you DFS, whenever we go to a node, we immediately mark it as visited. If you're not familiar with DFS, then maybe go check out a DFS video first, and then review the rest of this, because DFS is sort of like a prereq for this. Okay, so we have these in an array. Now what we're going to do is we're going to say, okay, for 3, we want to move forward 1 spot, and 3 is at index 0. So whenever we add an item to an array, to the vector or the array list, we're going to store the length at that, so we're going to say, okay, 6, when we've added 3 and 6, we want to add 4. Okay, the array is of length 2. So the index for 4 is going to be index 2. So now, when we want to know what is 1 spot beyond 4, we're going to look at index 2 plus 1 to get 3. What's 2 spots beyond? That's going to be 5, but then we take a mod, so it's going to give us location 3. So 1 step beyond is 7, 2 steps beyond is 3. So that is how we're going to detect cycles and find cycles in a graph where there only are cycles. And that'll solve this problem here. No? All right, perfect. So I'm gonna put this problem in the chat. Take a second to read it. So just to explain the problem real quick, we have a bunch of islands and they're labeled 1 through n. In the sample, we have 4 islands. Okay, and essentially what we're doing here is we have a sequence of moves that we're taking. So in the sample, it's left, left, right. And we're going to repeat this k times. And so then we're given a bunch of edges of like what the left edge and what the right edge is for every node. So, okay, let's say we just do a simple brute force here. So we start out at node 1, we then move left, left, right, and then we repeat it k times. That's all we're doing. Start at node 1, move in the sequence we're given. It could be different depending on the problem, but this is just a sample. Repeat k times. So, how should we potentially approach this? Well, let's consider the following. Let's say we do a brute force. So we're going to start at node 1, and then we're going to move m. We're going to do the m moves k times. It's going to be O of m times k. Given the values of m and k, this is going to be way too slow because m is up to 500 and k is up to 10 to the power of 9. So notice a pattern between this one and the previous one, right? We're still repeating something 10 to the 9 times. We're doing this something small and just repeating it a bunch of times. So we can actually apply a similar philosophy. But what we're going to do is we're going to start by computing for every node, where do I end up at after I do the sequence of m moves? So for one, when I do LLR, and I'm just gonna walk you through what LLR looks like because computing it doesn't really make any sense. So actually forget about the sample. Let's just say, let's draw our own test case. Let's say we have a few more nodes. So let's say after we start at node 1, if we do the sequence, whatever the sequence is, we end up at node 2. Node 2, we do the sequence, we end up at node 4. Node 4, we do the sequence, we end up at node 3. Node 3, do the sequence. I'm just going to draw some arrows here for us. Got something like this going. And just to draw this a little bit more cleanly, so essentially we have 1 which goes into node 2. And 2 is going to go into node 4. And then we have a cycle that goes to 3, 5, 6, 7, back to 4. Okay, so just to be clear on what the problem is asking, let's say we had in this case here, k equals 4. Well, we start at node 1, 1, 2, 3, 4. Our output will be node 5. Cool. Now, why is this problem harder than this problem here? What makes it more difficult? The thing that makes it more difficult is we can have this entrance before the cycle starts. So the cycle here is of length 5. What happens when k equals 20? Do we just do 20 mod 5? Well, that's not exactly right because we first have to reach node 4. First have to reach the cycle before we can do mod 5. So the entrance to the cycle is 2. 2 to enter the cycle. So we're going to do 20 minus 2 mod 5. So 18 mod 5 equals 3. So then we're going to be the third item on the cycle. 1, 2, 3, and we're going to be node 6. That's going to be our output. Any questions on this? Perfect. And again, I didn't really walk through the problem solving process on how we decided that we're just going to pre-compute what we do after all the M. That will be a different lecture on problem solving processes. In this lecture, we have a compressed 30 minutes. I want to make sure we really get into the permutation and cycle sort of stuff that we have planned for today. Okay, so the last thing that we sort of haven't yet covered is how do we implement this? How do we implement finding the length of the cycle and finding the X item in a cycle? Which we have to do for this problem here. So what we're going to do is we're going to have, so for every node, let's just say we store this graph. How do we store this graph? Let's just say we store this graph for every node, we're going to have next of I, which is the next node that you go to after node I. Actually, next is a keyword in C++, so I won't let you say that. So let's just say we call this go to I, which is the next node that you go to after node I. All right, so we're going to have DFS. We're going to have a function called DFS, and this is going to be our node that we're currently at. And I'm going to use pseudocode. You can do this in C++, Java, Python, doesn't really matter. Okay, so the first thing we're going to do is we're going to check, actually we're going to have several variables that we store for each of these nodes. So we're going to have a Boolean array for visited. It's going to be length n. And we're also going to have a Boolean array for open. And I'm going to explain what this is in a second. So visited is just your typical DFS, right? You, as soon as you start your DFS, you basically say, if we have already visited the node, then we're going to return. We've already visited it, don't worry about it. Okay, so what happens if we've not visited the node? The first thing we're going to do is mark it as visited. Cool. Actually, we don't even need the open for this problem. That's for more difficult problems. Okay. First thing we do is... Actually, hold on. We do need them open. My bad. Sorry. So we're not going to mark it as visited. So what we're going to do is... And let's just go over what the open sort of keeps track of. So we're DFSing down here. We're at node 1. We then go to node 2. We then go to node 4. If we reach a node that's already visited, what it means is, actually, we can remove the visited array and just use open. And the reason I'm going to call it open and not visited is because it has like a different definition of most visiteds. Okay, so what it means is that if we reach something that's currently open, so open means we've started the DFS for the node, but we have not yet closed it. That's all it means. So like at the beginning of the DFS, it's going to be open, and we're going to do some stuff, and then we're going to close. So open will just be false. If you've opened the node but not yet closed it, and we reach that node again, all that it means is that we have a cycle. That's all that means. So the first thing we do in our DFS is exactly what we just said. We open it. So we're going to say open node equals true. And the last thing we do in our DFS is open node equals false. And I'm going to put this here just because that's technically true to find cycles. And this will help you in problems which are more complicated. So you have like multiple stuff pointing in like this. Then you can just use the same framework I'm giving, or even something like this, where you can have an edge with multiple nodes pointing out. So you can use the same framework. You're also going to need to add visited for that framework, but that's just why I'm using the open, so that it generalizes to that. You have to add visited, but other than adding visited, it'll be basically the same. Okay, so you mark the node as open. Then we're going to have an array to keep track of, a vector or an array list to keep track of our cycle. So we're going to have, I'm just going to call this resizable array that can either be a vector or an array list to keep track of our cycle. So what we're going to do is we are going to add this to our cycle. There's a couple things that we want to do before we add this to our cycle. First, we want to check, is it already part of our cycle? So we're going to say, if it's already open, great. Now, we need to know the length of the cycle. How are we going to find the length of the cycle? The easiest way to find the length of the cycle is going to say, okay, what index did we add it in previously and what index are we at now? So for example, here, we add node 1, then 2, then 4, then 3, then 5, then 6, then 7, and then we have a node 4 to add. That's an ugly 4. But then we have a node 4 to add. And how do we know where to add the 4? Or how do we know the length of the cycle? It's going to be this length here. This is the number of items in the cycle. So then here we're essentially having our cycle len equals the current len of cycle to the length of our cycle resizable array minus the previous index. So how do we keep track of this? We're just going to have an array to store the previous index in the cycle array. So we're just going to say minus index of node. And then we return. And cycle length can be a global variable outside of the function. Cool. Otherwise, we're going to mark it open node equals true. Then we need to set the index that we're going to add it. So index node is going to equal like a len of cycle. Cool. And this will actually take care of everything for us. Let's review what we did in our DFS. If the node is already open, so if we found a cycle, then we're just going to mark the cycle length, and we are done. If we don't have a cycle length, then what we're going to do is we're going to say, okay, we're going to open up the node, we're going to mark the current index in it, and we're going to add it to the cycle. And that's about it. So that covers this problem, and it covers how to find the length of a cycle and the x item in a cycle, because we have this array, and you have the index of it, so you can just add x items to the index in the cycle variable to get the x item in the cycle. Or should get the x items after you. Thanks, guys, for attending. And yeah, I'll see you guys next week then.